Assalamualaikum warahmatullahi wabarakatuh. Okay, for today's lecture, we are going to cover chapter 8, okay, differential scanning calorimetry or DSC. So after finish this chapter, I will continue with TGA. Actually, TGA in the chapter 7, right? So we just skip one chapter because this chapter cover our experiment. Okay, for the first slide, let's look at the thermal analysis. Okay, DSC is types of the thermal analysis. So thermal analysis is a group of techniques that study the relationship between a sample property and its temperature. So the measurement of the changes in a material properties as a function of the temperature. So all thermal analysis is a series of techniques that are very useful for polymer characterization, and it measures the changes in physical and reactive properties of a material as a function of temperature and time. So basically, the study of the effect of heat on materials will obviously has a long history from man's earliest attempts at producing pottery, extracting metals, and making glass, followed by the development of thermometry and calorimetry. So all of the thermal analysis instruments have features in common, that is having a programmable temperature controller, an analysis module, and output devices. So example include of the thermal analysis, you can measure the weight loss on heating, stiffness or compliance, state changes, whether from solid to liquid, sample dimension, the chemical changes. The 5 main methods available commercially are we have differential scanning calorimetry, which measure the heat flow. We have also TGA, thermogravimetry analysis, which is measure the changes of the mass during the heat. And we also have TGDTA, which is thermogravimetry analysis and differential. Thermal analysis, it measures the thermal analysis of the material and also the mass and heat flow. We also have a TMA, thermomechanical analysis, which measure the dimension of the material when changes when effect the heat, and also dynamic mechanical analysis. The measurement of the changes in a material properties as a function of temperature, example, weight loss on heating, stiffness or compliance, state changes, okay, sample dimension, and also the chemical changes. Okay, now we look at the DSC theoretical background. Okay, for DSC we will cover, and the most important thing is about exothermic and endothermic process. So according to the classification, calorimetry is a technique for determining the quantity of heat that is either absorbed or released by a substance undergoing a physical or a chemical change. Such a change alters the internal energy of the substance. At constant pressure, the internal energy is known as enthalpy, which is H. So basically, in thermodynamics, the term exothermic process describes a process of reaction that release energy from the system, usually in the form of heat, but also in the form of light, electricity or sound. So exothermic, the arrow which is H will go downward. For example, the process of crystallization or decomposition. For endothermic, it is the process described a reaction which the system absorbs the energy from its surrounding, usually but not always in the form of the heat. And we look at the arrow will go upward for endothermic. So you need to remember the types of the arrow, whether going upward or downward, depending on the process, whether exo or endo. So for example of the endothermic reaction is glass transition, melting transition, and also evaporation process. With the enthalpy change between two states, so we have delta H. Delta H is the change of enthalpy between two states. whether solid to liquid or liquid to solid. While Cp is the specific heat capacity, it is the quantity of energy needed to change the temperature of 1 gram of material by increasing of 1 degree C at constant pressure. Sorry. Nt is the temperature, and Q is the heat flux, which is the quantity of heat transferred per unit time and mass. And we have nu, which is the heating rate. So the formula clearly shows that the relationship between the most important influential factors, namely the heating rates and the mass. So you need to have the temperature and the weight of the material to be measured. Okay, now we proceed with the DSC Theoretical Background. DSC measuring principle. The investigated specimen and the reference specimen are heated or cooled individually. So zero equilibrium principle is realized and should be permanently provide temperature equal to 0. The heaters will automatically adapt to the temperature changes between the investigated specimen and the reference specimen by supplying the additional power. And the difference between the power applied to the investigated specimen and into the reference specimen is measured as a function of temperature of and or time. So basically the DSC is a technique we use to study what happens to polymer when they are heated and also they are cold. We used to study what we call as a thermal transition of a polymer, which is the changes that take place in a polymer when you heat it. And the melting of a crystalline polymer is one example. So TG is also the thermal transition, and it need to heat by using DSC. So the pretty simple is most popular DSC designs. Okay, sorry. Okay, the most popular DSC design we can see at this picture. We have two pans sit on a pair of identically positioned platform connected to a furnace by a common heat flow path. So we can see that in one pan, you will put your sample here, and the other is reference pan. You leave it empty, so you can measure the changes of the temperature equal to the temperature of the reference minus with temperature of the sample. Alright. Okay, DSC plot. This is a DSC plot that you measure the TG and TM of the material. And the area under the curve, under the graph, is the delta H. Okay. And the x-axis is the temperature, while y-axis is the heat flow, which is measured in the unit of weight over gram. So the DSC plot will we need to set the constant heating rate with each the initial temperature and the final temperature you will going to use, and you need to set up the heating rate, how much the degree of the heating rate you need in your sample per minute. And the data is the heat flow to sample minus heat flow to reference versus time. Okay, temperature. So we can see that the yellow dip here is the curve for TG, which is 75. And this one is the curve for TC, which is crystallization temperature. And the last one is the TM, which is the melting point, 236.94. Polymer is an amorphous. TG will be like this. We will measure the change in heat capacity, which is means heat is absorbed by the sample polymer have higher heat capacity above the TG. So TG value is the value at the center of the incline here. Okay, kita ambil data point yang dekat center arah curve ni naik. So we take the middle of incline to be the TG. So change in the heat capacity is the amount of heat required to raise the temperature of an object, which is 1 degree C. Temperature change is different between the final temperature and the initial temperature. Now the most important thing is you need to see the heat flow arrow here. So when the heat flow, which is arrow is upward, so it is endothermic. Okay, if your heat flow is going downward, it will we can assume that it is exothermic reaction process. So if endothermic, the TG is going upward, dia akan macam menaik macam ni. Kalau arrow dia ke bawah, dia adalah exothermic. So TG dia bukan ke atas macam ni, dia akan turun ke bawah macam ni. So at TG, the heat capacity of the sample suddenly will increases, requiring more power to maintain the temperature the same. To show you some trick. So if you see the graph here, the label on the y-axis is the exothermic, which is the arrow must be downward. So the TG is also will the dip is going decline. Okay, so the value of the TG is the center of the decline, and TC will go upward, and the dip is upward like this, and this one is the TC value, and the last one is the melting temperature TM. So the dip for TM is going downward, and the dip for TC is going upward. And for the endothermic graph, okay, which is the process of the absorption, we can see that the TG, the value of the TG, the graph is going incline. The value of the TG is on the center, and TC, the dip of the TC is going downward. This is the reverse of the exothermic graph, and TM value is dip upward. Okay, I want you to remember these two different between the graph, so that if I give the value, you can plot your own graph, and you just need to decide whether you want to use the arrow exothermic, which is arrow downward, or endothermic, which is arrow upward. Proceed with crystallization temperature first. Now we look at the first step. At the right temperature for the crystallization to happen, material will have gained enough energy to move very ordered arrangement, which is it is in the crystal form. So at this stage, above TG, polymer will have a lot of mobility. So it will give off heat when this polymer falls into the crystalline arrangement. So you can see this is as a big peak in the heat flow versus temperature. So if polymer have the crystallization temperature, it will show the polymer that can crystallize. So for example, the atactic polymer like polystyrene, it won't get this peak because it cannot crystallize. Maybe ada yang akan appear, but the peak is not clear because the crystal structure is very weak. So the polymer form, the crystalline arrangement will give off heat, which is the exothermic reaction, and the area under the curve is, we call it as the latent heat of crystallization. Okay, I mean that the area below this curve, which is the area inside the curve. Okay, so the latent energy, or the latent energy of the crystallization, is actually the amount of the heat being given off when polymer is crystalline. So we call it as the exothermic process. Okay, now we look at the melting temperature. Okay, so melting temperature is endothermic because we have to add energy to the polymer to make it melt. So depend on the arrow you decided whether you want to decide it as going upward or going downward. So after the TG, the polymer have a lot of mobility. So the molecule is wiggle and squirm. When we keep heating the polymer, it will reach another thermal transition, which is melting, and it become melt. The polymer crystal begin to fall apart, and the chains come out of their ordered arrangement and begin to move freely. The melting transition, which is the absorbed energy, is the first order transition, and the temperature won't rise until all the crystal have melted. And the extra heat flow, which is show a large dip in the DSC plot. We can measure the area under the curve, which is the delta H, and also the melting temperature. So if we keep heating the polymer past its DC, we will reach the